Section 4.5, integrate functions using U substitution. What does that mean? Now, before I get to all this stuff, I want to do a problem really quick. And this problem, what if I asked you to find the derivative with respect to x of, let's see, how about 2x squared minus 5 raised to the third power? That's the problem I want. So if somebody said find that derivative, what would that derivative be? Well, that derivative, let's see. We'd start by bringing down the 3. Quantity, 2x squared minus 5 raised to the second power. And then we'd have to multiply that by the derivative of the inside function. Derivative of the inside function would be a 4x. So kind of crazy stuff. So there's a crazy derivative chain rule. So what if I instead asked a person to do the integral with respect to x of 3 times the quantity 2x squared minus 5 squared times 4x. So if we think about what would happen, the red problem should be the exact opposite of the blue problem. So if I asked you to do this, we would be able to reverse the process. And if I reverse the process, then in order to do this, well, let's see. I've got a quantity that's being raised to the second power. But inside that quantity, I have 2x squared minus 5. But inside that quantity, here's 2x squared minus 5. But, oh, interestingly enough, there's the derivative of 2x squared minus 5. And so if you wanted to integrate something 3 times something to the second power, well, that would end up being something to the third power. So what I'd end up with here would be 2x squared minus 5, quantity cubed, plus c. And if you wanted to check the blue answer, you could take the derivative. So point I'm trying to make with all this information is, if we take the derivative of something and we have to use chain rule, we're going to use this integration by substitution stuff, this thing we're going to call U substitution, to reverse the chain rule. But now the tricky thing is going to be, in order to do chain rule, first off, what you have to have is you're going to be looking for a function inside of another function. A function inside of another function. So like what we have right here, what I notice in this blue one, there's an inside function. That inside function is going to be what we're going to call U. But in order for this to work, you have to have the derivative of U in the problem also. So when we look at this, the way I have this theorem written down over here, this is going to be a little bit crazy. It might actually make more sense if I looked at it this way. If you look at what happens over here on the right-hand side, we have capital F of g of x plus c. If I asked you to find the derivative, what's the derivative of capital F of g of x plus c? Well, what's that derivative? Let's see. That derivative would be capital F, well, capital F prime. Capital F prime is the same as lowercase f of g of x. Whoops, sorry, of g of x, not of g prime. I'm doing chain rule. G of x is inside, so first do the derivative of a capital F, which should be f of g of x, times the derivative of the inside function, which should be g prime of x, plus the derivative of c, which would be 0. If you look at what I have right here, it matches exactly with what I have right there. So what is the antiderivative of this? First off, what you guys are going to be looking for. You are going to be looking for an inside function. So g of x is your inside function. What we would do in this problem is we would say u is equal to g of x. And then what we're going to do is we've got to make sure that g prime of x is in the problem also. du over dx, that's supposed to be a u. du over dx would be g prime of x. Well, here's g prime of x. You have to have both of those things in the problem in order to be able to do a problem by U substitution. Now, this is one of those things that's really very hard to talk about. Once you see it a couple times, I think you're going to find it's not too bad. So let's look at problem number 1. Do you see a function inside of another function? I do. I see x squared plus 1 inside of something to the fifth. And then I see this other goofy x written out there that doesn't look like it makes any sense. So we're going to say u is equal to x squared plus 1. Now, what is the derivative of u with respect to x? du over dx. Well, that would be 2x. Now, here's your challenge. If you're going to do an integration problem by substitution, your challenge is, quickly as you can do it, is to try to represent the problem using all u's and no x's. So what we want to do right now is we want to rewrite the problem in terms of u. And that's a little note right here, no x's. That's your job. Okay, rewrite the problem in terms of u with no x's. Well, so let's see. So I have a couple of things here. I'm gonna rewrite this. du, if I was separating variables, I would have 2x times dx. Okay, let's look at what we've got in the problem. Now, some people will say, all right, let's take all the x's in the problem and see if we can replace them. Well, first off, I see an integral symbol, and I see a quantity that's being raised to the fifth power. What did we call that quantity? Well, we just called that quantity u. Okay, so that's taken care of. But now I also see an x and a dx. Well, what is x dx the same as? Oh, look, there's an x dx right there. What's x dx the same as? Well, that looks to me like it would be exactly the same as a half of a du. So now, if our challenge is to rewrite this problem so we don't have any x's in it and we only have u's, then what I would put right here in place of the x dx would be a 1/2 of du. So we just changed this problem. It has no x's in it. It has only u's in it now. So if I rewrite this, let's see. So that 1/2 is a constant. Let's pull it to the outside. Integral u to the fifth du. Is that an integral we know how to do? You bet. And not only that, it's a nice integral that we know how to do. 1/2. Add 1 to the power, divide by the power. Don't forget c. Now, the original problem had u's in it, or didn't have any u's in it. It had x's in it, so let's reverse the process. 1/12, something to the sixth, plus c. What's the something? X squared plus 1. And you just did your first integration by substitution. The key is what's in green. Rewrite the problem so that you have all u's and no x's. And when you rewrite it, you'll have a nice new problem over here, hopefully, that we can integrate. Okay, let's look at problem number 2. Problem number 2. Well, let's see. Do we have a function inside of another function? Yeah, I think we do, because here it looks to me like there's a 5x that's inside of cosine. So if there's a 5x inside of cosine, let's make u equal to 5x. That's my inside function. So du over dx would be 5 dx. Now, I happen to see right now that there is a 5 dx in the problem already. So if I go to rewrite this thing, well, let's see. 5 dx. Whoops, I'm sorry. I got a step ahead of myself. This should be a 5. Then when I separate my variables and multiply the dx to the other side, there's my 5 dx. What's 5 dx the same as? 5 dx is exactly the same as 1 du. So rewrite the problem. Integral symbol. I've got a cosine of something. What's the something? That something is now u. And what am I putting in place of the 5 and the dx? In place of the 5 and the dx, I can put 1 du. I've rewritten the problem. It's all in terms of u. Is it an integral we know how to do? You bet it is. Whose derivative is cosine? Sine. Don't forget your c. Now, did the original problem have u's in it or x's? It had x's, so let's rewrite it. Sine of that 5x we started with plus my c. And if you want to check it, take the derivative of what's in that red box. What's the derivative in the red box? Derivative of sine is cosine of 5x times another 5, and you go back and look at the original problem, and it looks exactly the same. So there's a couple of them. Whoops. Let's look at 3 and 4. Problem number 3. Do you see a function inside of a function? Yes. U x cubed plus 1. What do I do with the rest of the stuff? I don't know. Hopefully I can make it disappear. Du over dx. Well, what's that? That's 3x squared. So du is the same thing as 3x squared times a dx. Challenge. Rewrite the problem. I've got an integral symbol. I've got a quantity being cubed. What's that quantity? That quantity is u. But I've also got an x squared and a dx in the problem. What am I going to do with that? Oh, look, here's an x squared and a dx. What's that x squared dx the same as? It's the same as 1/3 of a du. So in place of that x squared dx, let's put a 1/3 and a du. Rewrite the integral. Is one we can do? You bet. 1/3 integral u cubed du. Simple integral way back to the beginning of learning how to do antiderivatives. 1/12 quantity to the 4th plus c. What's the quantity? X cubed plus 1. Another successful u substitution. All right, now this number 4 is going to be tricky because number 4 we should probably start. Let's rewrite the problem so it looks the way that it should. We're really integrating here sine of 3x, which is being squared, times the cosine of 3x dx. Now, a lot of people are going to look at that and say, we should make u equal to 3x. And if you make u equal to 3x, it'll be a start, but it's not going to hit the root of the problem. The root of the problem is this nastiness with sines and cosines. What I'm going to say is, look what's inside of here. Sine of 3x is being squared. That sine of 3x is going to be your u. So du over dx. Derivative of sine, cosine of 3x, derivative of 3x times 3. Separate your variables. 3 cosine 3x dx. Do we have that in the problem? Look at here. Cosine 3x dx. I've got that right here. What's that the same as? Cosine 3x dx is the same as 1/3 of a du. So replace the blue with the third of a du. Rewrite your integral. Integral? Well, what's being squared? Looks like u is. Interesting. What's the blue thing? That's the same as 1/3 of a du. Is that an integral we can do? You bet it is. 1/3 integral u squared du. 1/3 times 1/3 u cubed plus c. 1/9 quantity cubed plus c. What's my quantity? Sine of 3x. And if you wanted to check it, you could take the derivative of that problem, and you get the same thing that we started with originally. Integration using u substitution.